Okay, in this video, we're going to be changing parametric equations back to a rectangular or an XY coordinate system form. It's very simple. It's going to remind you a lot of substitution when we're solving using substitution to solve a system. Pretty much the method is going to be very, very similar to that. And here's your rules. To write a parametric equation in rectangular form, you must eliminate the perimeter. So again, very much like substitution elimination. Use the following process. We're going to solve either equation for t, and we're simply substituting it into the other expression for t, and then we're going to simplify. So let's do that here. You have a parametric equation, x equals 4t minus 1 and y equals 6 minus t. It says write each parametric equation in a rectangular form. Note any restrictions in the domain. So we got to be careful there of any domain restrictions. So again, all we do is we're going to solve either one of these for t, and it's going to be much easier to solve here, this equation for t. What I'm going to do is I'm going to move my t over, and I'm going to move my y to the other side here. So I get, this will turn into t is equal to, I believe that would be 6 minus y or negative y plus 6. You can write it either way. And then we're simply plugging that in for t over here. So my other equation now turns into x equals 4 times. The value of t is now 6 minus y, so plug that in for t. And then you have minus 1. Let's now clean it up. So you have x equals 24 minus 4y minus 1. We can combine some like terms here. Gives me x equals 23 minus 4y. And now it's simply just solving it for y. You've eliminated your t, and now let's get y by itself. Move the 23 over. Gives you x minus 23 equals negative 4y. Then you can divide by negative 4. And it gives you y is equal to, you can leave it like this if you would like to, x minus 23 over negative 4. Or since this is a linear equation, let's go ahead and split this. You got a 1 in front of the x. Let's divide each of these by negative 4. Gives you y equals, the 1 divided by negative 4 would be negative 1/4 x. And then a negative 23 divided by negative 4 would be a positive 23/4. And you see that when you combine them, you can graph it either way. If you graph it as a parametric, or if you graph it in this form, you're going to get the exact same line. Okay, the next one, x equals t squared plus 5 and y is equal to 3t. Much easier, obviously, to get the t by itself over here. So let's go ahead and move the 3, and it gives you that t would equal y over 3. So in the other equation, simply plug that in for t, and it gives you x is equal to, in the place of t, we're putting y over 3 squared plus 5. Let's square both the y and the 3. That gives you x equals y squared over 9 plus 5. And now it's simply getting, again, y by itself. Let's move our plus 5 over by doing minus 5. So that gives you x minus 5 equals y squared over 9. Get rid of the 9 by multiplying. It gives you 9x minus 45 is y squared. And make sure when you get rid of that squared, you do, and I'm going to put the y first, y is equal to get rid of a square, don't forget your plus and minus square root. So plus and minus the square root of 9x minus 45. Now that can be simplified. We can leave it like that. But since that 9 can factor out of that, you can do this either way. I'm going to split that and write it as plus and minus the square root of 9 times x minus 5. And then that 9 can be brought out front because you can find the square root of 9. So we can simplify that expression. So you could actually also write it as plus and minus 3 times the square root of x minus 5. Either method would be fine. Number 3. Again, we've got to solve one of these for t. Since this is linear expressions or equations will always be easier to solve for t. So let's move the 1 and the negative 4 over. Move the 1 over by subtracting. And then we're going to move the negative 4 over by dividing. So you get t is x minus 1 over negative 4. Let's plug it in the other expression or equation in the place of t. So it gives you 2 times t, which is x minus 1 over negative 4 squared plus 5. Let's square both the top and bottom. Now you got to be careful here because when you square the top, it's a binomial. So squaring the top would give you x squared minus 2x plus 1. Squaring the bottom would give you a 16. So you got to make sure that you FOIL that out when you square it. The 2 and 16 will cancel and leaves you with an 8. So you have y equals, and you can actually just split that up if you would like to now and divide everything by 8. So that'd be 1/8 x squared minus 2 divided by, 2 divided by 8 would be 1/4 x, and then 1 divided by 8 would be plus 1/8, and then plus 5. And then we can combine these two, and that would give me y is equal to 1/8 x squared minus 1/4 x, and let's see, that'd be plus a 41/8. So the hard part here is really not the changing it to rectangular form. The hard part is just the algebra. Next one, let's solve our linear expression over here for t. So move the 7 and the 2 over, and it gives you that t is equal to, when you move 7 over, it'll be a plus 7, then we got to divide by 2. Plug that into your other expression for t, so you now have x equals t, which is y plus 7 over 2 squared minus 3. Square the top. Make sure that you FOIL it out when you square it. So that'd be y squared. You know what? Since I'm having to get y by itself, it's going to be much easier to do this because I just noticed that when I square that out, I'm going to have y squared plus I'm going to have, I'm going to end up with a y term as well. So here's what I'm going to do. I'm going to leave the top as y plus 7 squared, and I am going to go ahead and square the bottom. That would be a 4. And that's what I now have. And it's going to be much easier to get y by itself leaving it in that form. Okay, watch what I do. Take the minus 3 and move it over, and you now have plus 3 equals y plus 7 squared over 4. Now we're going to move our 4 over, and that's the reason I went ahead and squared it out. Move the 4 over by foiling, or you can leave it as 4 parentheses x plus 3 because I'm looking ahead about what's about to happen. Because now I got to take the square root of that. To get rid of this square, I got to do plus and minus the square root. And since that was a 4, I just left it so that I can split that and clean it up. So you now have plus and minus. The square root of 4 is going to be 2 root x plus 3, if you go ahead and simplify that, equals y plus 7. And then the very last step, to get rid of plus 7, we just got to do minus 7 on the other side. So you have y equals negative 7 plus and minus 2 root x plus 3. There you go. Okay, number 5. We have some restrictions here. Now we got to be a little bit careful with those restrictions. So let's go ahead and plug our t value in and simplify that first. Then we'll talk about those restrictions in just a second. So this is our linear term. Let's move our 3 over. That'd be x plus 3 equals 1/2 t. Get rid of the 1/2 by multiplying by the reciprocal, which is 2. So that would be that t is equal to 2x plus 6. Now let's plug that into our other one, 4t, and I now have y equals 2x plus 6 squared minus 7. Let's go ahead and square that out. It gives you, again, shortcut for squaring is to square the first, multiply the 2 and double it. That's going to be plus 24x, and then square the last. That'd be plus 36. And then let's go ahead and combine that 36 plus or minus 7 so we don't have to rewrite it, and that'd be plus 29. So there's what you have. However, we do have a restriction. T is only between 2 and 8. However, normally our restrictions are domain restrictions. They're X restrictions. So we want to know where, not where my T is restricted, but where my X is restricted. So how are we going to figure that out? Well, just plug these T's into our X parametric equation. When you plug in 2, you get X is equal to 1/2 times 2 minus 3, which is 1 minus 3 or negative 2. So that means a T value of 2 would correspond with an X value of negative 2. And a T value of 8 would be 1/2 times 8 would be 4 minus 3, which is 1. So a T value between 2 and 8 is the same thing as an X value between negative 2 and 1. So that's all we have to do on our domain restriction. So the next one, doing the same thing. Now this one's not going to be as easy to get by itself because you have T squared. However, here's your trick. Let's go ahead and instead of solving this thing for T, why not solve it for t squared and just plug that into the other one? So move the 4 over, it gives you x plus 4 is equal to t squared. And since I have a t squared right here, let's plug that in. So you have y equals x plus 4 plus 1. And those parentheses are not necessary. So let's go ahead and clean it up, and you get y equals x plus 5. So very easy if you do it that way. Now your t values are restricted between negative 1 and 4. So let's see where our x values are restricted. When you plug in -1 into your x, it gives you 1 minus 4, which is -3. Now, again, we are changing these t's to x's now. When you plug in 4, it gives you 16 minus 4, which is 12. So that means your x values are restricted between -3 and 12. Number 7. Now we do have a t restriction here. T, I noticed that you have a t on the bottom of a fraction. T cannot be 0. So you got to be careful with that. So you do have that restriction. So let's go ahead and solve this thing for t. We can actually just flip-flop these, and that gives me that t is equal to 1 over y. So everywhere I have a t in my other expression, I'm going to plug in 1 over y. So I have x equals 1 over y plus 2 over 1 over y. Now I think if I went ahead and flipped and multiplied this thing, it might go ahead and clean it up for me. So to divide by 1 over y, we're going to multiply by y over 1. And I notice when I do that, it's going to cancel out my y's in my first expression. So that's the reason I'm going ahead and doing it now. Y over 1 times 1 over y just gives me a 1. Plus 2 times y would be 2y. So that cleaned up really nice. So now let's get y by itself by moving the 1 over first. So you have x minus 1 equals 2y. Get rid of the 2 by dividing by 2. And I'm going to go ahead and distribute that, and that's going to give me y equals 1/2 x minus 1/2. Okay, now let's talk about that domain restriction. There's a couple of different ways we can look at this. Let's go ahead and look at it one way to where I can review a little bit for you. So x equals t plus 2 over t. If you remember correctly, if you treat this like y's and x's, if you were to graph this, because of t being 0, t is a factor of the bottom but not a factor of the top, you're going to have a vertical asymptote line at that value of 0 if you were to graph this. So you're going to have a domain restriction, a t restriction at 0. And if you were to graph it, it would look something to this effect. At 0, it would come up, and then it would pull this number on the other side. And I knew what it looked like because not only do you have a vertical asymptote, but you have a horizontal asymptote as well. If you remember, the way we found horizontal asymptotes is if the powers on top and bottom are the same, we looked at the leading coefficients, and we would have a horizontal asymptote at x equals 1. Now, this is a tx graph, not an xy graph. So that vertical asymptote at 0 created this x asymptote, right here at 1. So therefore, that's going to be your restriction on x. The restriction of t not being able to be equal to 0 created an x restriction of 1. So that's going to be what x can equal. Or here's the other way of doing it. We could have actually took and solved, let me erase all this. We could have took this first equation and solved it for t, and that had been xt equals t plus 2. Move the t's all to the same side, so that'd be xt minus t is equal to 2. Let's factor that t out. You got t times x minus 1 is equal to 2. And then when you divide by x minus 1 to get t by itself, you get t is equal to 2 over x minus 1. And you can see that you are going to have a restriction here that x cannot equal 1. That's probably going to be the easiest way of doing it. So there is your domain restriction. Okay, number 8. Let's do the same thing. It's easier to use our linear expression or equation over here. So let's move the 8 over. It gives you y minus 8 is equal to 1/2 t. Let's move our 1/2 over by flipping and multiplying. Gives you 2y minus 16 is equal to t. Now let's substitute that into our other equation. And I now have x is equal to the square root of t, which we do not need any parentheses here. That's 2y minus 16 minus 3 plus 5. And then this minus 16 minus 3 can be combined into minus 19. Let's now try to get that y by itself. So move your 5 over. It gives you x minus 5 is equal to the square root of 2y minus 19. To get rid of a square root, we're going to square. So I now have x minus 5 squared. And I'm going to leave it like that to where we have that transformation form that's easier to work with. Let's get rid of the 19 by moving it over. That'd be x minus 5 squared plus 19. is equal to 2y. Now you got to be careful because to get rid of this 2, you have two terms on the other side. To get rid of this 2, you're going to have to divide each of those terms by 2, or I'm actually going to flip and multiply there and write it as 1/2 times x minus 5 squared plus, and instead of writing that as 1/2 times 19, I'm going to go ahead and take half of it, and that would be 19 halves. And that is equal to y. So therefore, there is your parabola, and that parabola is in the correct form. Now, we did have a restriction up here. You have a radical, so that means that t, the value of t, if you were to plug it in, you cannot take the square root of a negative. So if you plug in things like 1, 2, 4, well, actually 0, -1, negative, all those would give you negatives under that radical. All values, let's see, that would be all values below 3 would give you a negative. So therefore, t would have to be a value greater than or equal to 3. Okay, now let's find our restrictions for x. Now, again, if you'll think about it like this, think about transformations and look at this graph. And instead of x's and t's, I want you to think back, what would we have done if this was x's and y's? What it would we would have looked at if we had y equals the square root of x minus 3 plus 5. Okay, we had domain restrictions, we had range restrictions here. Okay, this graph would look something like, let's say it's a square root function that's been moved right 3 and up 5, and it would look something like this. So what you can actually do is you can think, okay, go back to the original. We had a t restriction of t would have to be greater than or equal to 3, which was just like, if we looked at this, an x value that has to be greater than or equal to 3. What about our range? If it's a square root function, again, it's going to look something like this. However, the way I've got this graphed is, if you go back to your original, we have t's and x's. So this would be your t's, these would be your x's. Your t's, again, would be restricted from 3 to infinity. Your x's are restricted from here up, or your graph starts at this value and goes up. And there's a couple of different ways to do this. You could plug in 3, or you can just think about your transformations. This has been moved right 3 and up 5. That's a y value of 5, or in this case, it's an x value of 5. So therefore, our x values are going to be, if t is restricted greater than or equal to 3, that means x is restricted to greater than or equal to 5. So again, just use those principles that we've done before. Pretty much you found domain and range of this. The inputs are the t's, the outputs are the x's. Find the domain, find the range, and that range will tell you what your x's are restricted to. Okay, next up, polar and parametric equations. The graph of a polar equation, which again, remember, polar has r's and thetas instead of x's and y's. The graph of a polar equation, r equals f of theta, is the same as the graph of a parametric equations. X equals f of theta, which remember that f of theta is r. So if r is equal to f of theta, then x will be f of theta, which is r times cosine theta. Which again corresponds, remember, x equals r cosine theta, y equals r sine theta. So pretty much all we're doing is instead of r's, we're sticking in those f of thetas in their place. So there you go. So x equals r cosine theta or f theta cosine theta, and y equals r sine theta or f of theta sine theta, where r is the parameter. So what we're asked to do now is let's write each polar equation as a pair of parametric equations. And this is actually pretty simple. Remember again that x is equal to r cosine theta, y is equal to r sine theta. So therefore, we could just say x is equal to, that's our parametric equation, x is equal to r cosine theta. Let's try that again, theta. And our y value will equal r sine theta, because they pretty much just tell you, hey, r is 3. So therefore, there you go. So in this case, our r, or our f of theta, is 4 sine theta. So our x in our parametric equation will equal r times cosine theta, and our y will equal r times sine of theta. Now, since you have a sine times a sine, we could actually just write that as sine squared theta. And if you were to graph these as a parametric equation, again, it would give you the exact same graph as this would before. Now, I do want to show you something that these parametric equations actually can also be graphed on Desmos. Notice what I've done here. This is my first graph, 3 cosine theta, 3 sine theta. One thing that you do have to do is instead of using thetas, you do have to use t's to get them to graph in parametric. But all you do is actually write them as a point. I put them in parentheses, put a comma between them because this is your x and this is your y. So therefore x equals this, y equals this, and just graph it. And you do see that you have a circle, which is the same thing as r equals 3. The second one did the same thing. You had 4 sine t cosine t, or actually 4 sine theta cosine theta, and then 4 sine squared theta was also a circle that had been translated up, looks like 2 units. And notice I graphed from 0 to 6.3, which is about 0 to 2 pi is what I did. And that's how you graph by using Desmos. Okay, the next few problems says write each pair of parametric equations in rectangular form. So we're going to eliminate the parameter. On the last one, we took this equation and we wrote it as an x and a y. Now we have our x and y's and we want to write it as a single parametric equations. Note, it says trigonometric identities you're going to use to eliminate the parameters. So let's see what we can do with this first one. You have x equals 3 cosine theta, y equals 2 sine theta. Now, here's what's going to be tricky here. You do have to use a trigonometric identity. We need to find some sort of relationship between cosines and sines. Now, it's an obvious one. We know that cosine squared of an angle plus sine squared of the same angle is always equal to 1. So what we're going to do is we're going to take these x and y values up here and we're going to solve them for cosine and sine. So we know that the cosine of theta from our first one is equal to x over 3. And we know that the sine of theta from my second parametric equation up here is equal to y over 2. So all we're going to do is going to take this trig identity, which we know relates cosines and sines, and we're going to plug in what cosine and sine is now equal to. And then we have completely removed our cosines and sines. So since the cosine is x over 3, then cosine squared will be x over 3 squared plus sine squared will be y over 2 squared is equal to 1. And now we have it in x in terms of x and y's. So that'll be x squared over 9 plus y squared over 4 is equal to 1. And if you don't remember, that would be an ellipse. The next one. Same thing. Let's solve each of these for sines and cosines, and we're going to plug it in just like we did that one. We know that the sine of theta would be x over 5. And by our second equation, the cosine of theta will be y over 8. We know that, again, cosine squared theta plus sine squared theta is equal to 1. So therefore, cosine squared will be y over 8 squared when you plug it in. Sine squared will be x over 5 when you plug it in. So then it looks like we're going to have another ellipse. Have y squared over 64 plus x squared over 25 will equal 1. Number 13 looks very similar to it, except for you have x equals sine squared and y equals 4 cosine. So what we can do is use that same sine squared plus cosine squared is equal to 1. Let's go ahead and solve the second one, though. The cosine will equal y over 4. So now we have cosine squared plus sine squared is equal to 1, which is the one that we're going to use a good bit. Now notice here it says sine squared is equal to x. So we're just going to take that sine squared out completely and put an x in its place. We know that cosine is y over 4. So cosine squared will be y over 4 squared, and that's equal to 1. So in this case, we're not going to have an ellipse in this one. We have y squared over 16 plus x is equal to 1. So we can solve this thing for x by moving the y squared over 16 over. And let's write it like you're used to seeing it. When you move it over, it's going to become a negative. It's a positive over here. So let's write it as a negative. And instead of y squared over 16, let's write it as 1/16 y squared. And then you have the plus 1. So you have a parabola. And again, that parabola is a sideways turn parabola. And you could even set the thing out front equal to the 1 over 4p. You could find all that stuff. Now, number 14, a little bit different. Notice you have an x value of cosine 2 theta. So we're going to have to find some trig identity that relates cosine 2 thetas with cosine thetas, and that's going to be your double angle identity. Let me pull up my identity sheet. And once we get it pulled up, let's find something that relates double angle identity cosine with just plain cosine theta. Let's go down to my double angles. And here it is. And here is an identity that relates cosine of 2 thetas with cosine thetas. So let's go ahead and copy that over. And there we go. Cosine of 2 theta is equal to 2 cosine squared theta minus 1. We know that this is always a true statement. So therefore, in the place of cosine 2 theta, I can replace it with an x equals 2 times. In the place of cosine, we can replace it with a y, but this is cosine theta or cosine squared theta, so that's going to be y squared, then minus 1. And again, you're done. X equals 2y squared minus 1. You can leave it like that. That is a sideways parabola. If you would like to solve it for y, you can move the 1 and 2 over. That'd be x plus 1 divided by 2 equals y squared. So therefore, y would equal plus and minus the square root of x plus 1 over 2. Either one of those answers would be fine.